Hi everyone, welcome to this channel where I share my ideas through my voice. In today's podcast, I want to talk about quantum computing, a rapidly emerging technology that harnesses the laws of quantum mechanics to solve problems too complex for classical computers. You may have heard of quantum computers from the news or sci-fi movies, but what are they exactly and how do they work? In this post, I will try to explain the basics of quantum computing casually and simply, without getting into too much math or jargon. What is quantum computing? Quantum computing is a way of using quantum phenomena, such as superposition and entanglement, to perform computations that would be impossible or impractical with classical computers. Quantum phenomena are weird and counterintuitive behaviors that happen at the smallest scales of matter, such as atoms and electrons. Quantum computing is one of the most exciting and cutting-edge technologies of our time. It promises to revolutionize many fields of science, engineering, and business by harnessing the power of quantum physics to perform computations that are impossible or impractical for classical computers. But what is quantum computing exactly? How does it work? And what can it do for us? In this podcast, I will try to answer these questions and more, using simple and accessible language. Let's dive in. What is quantum computing? Quantum computing is a way of processing information using quantum mechanical phenomena, such as superposition and entanglement. These phenomena allow quantum computers to manipulate bits of information, called qubits, in ways that classical computers cannot. A classical bit can only store one of two values, 0 or 1. A qubit, on the other hand, can store both 0 and 1 at the same time, in a superposition state. This means that a qubit can represent more information than a bit and that a quantum computer can process multiple possibilities simultaneously. For example, suppose we have 2 bits and 2 qubits. The 2 bits can store one of 4 possible combinations, 00, 01, 10, or 11. The 2 qubits can store all 4 combinations at the same time, in a superposition state, 00 plus 01 plus 10 plus 11, SQRT, 4. This gives the quantum computer an advantage over the classical computer, as it can explore all 4 options in parallel. Another quantum phenomenon that gives quantum computers an edge is entanglement. This is when 2 or more qubits are linked in such a way that their states depend on each other, even if they are physically separated. This means that measuring one qubit will instantly reveal the state of the other qubit, without any communication or interaction. For example, suppose we have 2 entangled qubits, A and B. If we measure A and find it to be 0, we will instantly know that B is also 0. If we measure A and find it to be 1, we will instantly know that B is also 1. This allows quantum computers to perform operations on multiple qubits at once, without having to access them individually. How does quantum computing work? Quantum computing works by applying quantum logic gates to qubits. Quantum logic gates are operations that change the state of one or more qubits according to certain rules. For example, a NOT gate flips the state of a single qubit from 0 to 1 or vice versa. A CNOT gate flips the state of a second qubit only if the first qubit is 1. By combining different quantum logic gates, we can create quantum algorithms that perform specific tasks on qubits. For example, one of the most famous quantum algorithms is Schia's algorithm, which can factor large numbers into their prime factors much faster than any known classical algorithm. This has important implications for cryptography, as many encryption schemes rely on the difficulty of factoring large numbers. However, quantum computing also faces many challenges and limitations. One of them is decoherence, which is when qubits lose their quantum properties due to interaction with their environment. Decoherence introduces errors and noise into quantum computations, which can render them useless or inaccurate. To prevent or correct decoherence, quantum computers need to use techniques such as error correction codes, fault-tolerant designs, and low-temperature cooling systems. These techniques increase the complexity and cost of building and operating quantum computers and limit their scalability and availability. Another challenge for quantum computing is finding practical applications that can benefit from its advantages over classical computing. While some problems are known to be easier or faster to solve with quantum computers than with classical computers, such as factoring large numbers or simulating quantum systems, many other problems are still unknown or unclear. Moreover, some problems may not require quantum computing at all, as they can be solved efficiently with classical algorithms or heuristics. For example, machine learning and artificial intelligence are often cited as potential applications for quantum computing, but they also rely on data analysis and optimization techniques that can be performed well with classical computers. Therefore, finding the right problems and solutions for quantum computing is an ongoing research area that requires collaboration and innovation across disciplines and domains. One of the key concepts in quantum computing is the qubit, which stands for a quantum bit. A qubit is like a bit in classical computing, which can store either 0 or 1, but with a twist. A qubit can also be in a superposition of 0 and 1, meaning it can be both at the same time. This gives qubits more flexibility and power than bits, as they can encode more information and process it in parallel. Another important concept is entanglement, which is a special kind of connection between two or more qubits. When qubits are entangled, they share their quantum states and act as one unit, even if they are physically separated. This means that measuring one qubit will instantly affect the other qubits, regardless of the distance between them. This allows quantum computers to perform complex operations that involve multiple qubits at once. Why do we need quantum computers? Quantum computers have the potential to solve some of the hardest problems in science, engineering, cryptography, and artificial intelligence. These are problems that classical computers cannot handle efficiently or accurately because they involve too many variables, too much data, or too much uncertainty. For example, quantum computers could help us design new materials and drugs by simulating how atoms and molecules interact with each other. They could also help us break encryption schemes that protect our online data and communications by finding hidden patterns and factors. They could also help us create more intelligent and creative machines by exploring new possibilities and learning from data. However, quantum computers are not magic machines that can do everything better than classical computers. They are only good at certain types of problems that require quantum logic and algorithms. They also have many challenges and limitations that make them hard to build and use in practice. What are the challenges and limitations of quantum computing? Quantum computing is still a very young and experimental field that faces many technical and theoretical hurdles. Some of the main challenges are building high-quality qubits that can maintain their quantum states for long enough without being disturbed by noise or errors. Scaling up the number of qubits and connecting them reliably and efficiently. Developing quantum algorithms that can exploit the advantages of quantum computing while avoiding its drawbacks. Creating quantum software and hardware that can interface with classical systems and users. Currently, there are only a few quantum computers in the world that have achieved some level of quantum supremacy, which means they can perform tasks faster or better than any classical computer. However, these machines are still very limited in their capabilities and availability. They are mostly used by researchers and developers who want to explore the potential of quantum computing and test new ideas. How can I learn more about quantum computing? If you are interested in learning more about quantum computing, there are many resources available online that can help you get started. Here are some of them. IBM Quantum Experience, a platform that lets you access real quantum hardware and software through the cloud. You can run experiments, learn tutorials, join challenges, and join a community of enthusiasts. Qiskit, an open-source framework for creating and running quantum programs on various backends, including simulators and IBM quantum devices. Microsoft Quantum, a platform that offers tools, libraries, services, and education for developing quantum applications on Azure Cloud. Google Quantum AI, a platform that provides access to Google's quantum hardware and software, as well as research papers, podcasts, videos, and courses on quantum computing. Quantum Computing Stack Exchange, a question and answer site for engineers, scientists, programmers, and students who are interested in quantum computing. I hope you enjoyed this post and learned something new about quantum computing. If you have any questions or comments, feel free to leave them below. Quantum computing is a fascinating and rapidly evolving field of technology that promises to revolutionize many areas of science, engineering, and business. Quantum computers are devices that use the principles of quantum mechanics, such as superposition and entanglement, to manipulate information in ways that are impossible for classical computers. Quantum computers can potentially solve certain problems much faster than classical computers, such as factoring large numbers, simulating complex physical systems, and optimizing combinatorial problems. However, quantum computing also faces many challenges and limitations. One of the main challenges is to build and maintain high-quality qubits, which are the basic units of quantum information. Qubits are very sensitive to noise and interference from their environment, which can cause them to lose their quantum state and introduce errors in the computation. To overcome this problem, quantum engineers have to design sophisticated methods of error correction and fault tolerance, as well as use advanced materials and technologies to isolate and control qubits. Another challenge is to develop efficient and scalable quantum algorithms that can exploit the power of quantum computers. Quantum algorithms are different from classical algorithms in that they use quantum logic gates and operations that can manipulate multiple qubits at once. Quantum algorithms also have to take into account the probabilistic nature of quantum measurements, which can only reveal one possible outcome of a superposition state. Quantum algorithms have to be carefully designed to maximize the probability of obtaining the correct answer and minimize the resources required. Quantum computing is still in its infancy, but it has already attracted a lot of attention and investment from academia, industry, and government. Many companies, such as IBM, Google, Microsoft, Amazon, and Intel, have developed their own quantum hardware and software platforms, and offer access to their quantum devices and services through cloud-based platforms. Many universities and research institutes have also established dedicated quantum computing centers and laboratories, where they conduct cutting-edge research and education on various aspects of quantum computing. Quantum computing is an exciting and promising field that has the potential to transform many domains of human endeavor. However, it also poses many technical and practical challenges that require continuous innovation and collaboration. Quantum computing is not a magic bullet that can solve any problem, but rather a new paradigm that can offer new perspectives and opportunities for solving some of the most difficult problems in science and society. Quantum computing is a fascinating and rapidly evolving field that promises to revolutionize many areas of science, technology, and society. Quantum computers use the principles of quantum mechanics, such as superposition and entanglement, to manipulate information in ways that are impossible for classical computers. Quantum computers can potentially solve problems that are too complex, too large, or too time-consuming for even the most powerful supercomputers today. But what is the current state of quantum computing and what are the challenges and opportunities for its future development? In this podcast, I will give you an overview of some of the key aspects of quantum computing, such as: what are the main applications of quantum computing? What are the main types of quantum computers and how do they work? What are the main obstacles and limitations of quantum computing? What are the main trends and milestones of quantum computing? Applications of quantum computing. Quantum computing has the potential to impact many domains and industries, such as cryptography, chemistry, material science, agriculture, and pharmaceuticals. Some of the possible applications of quantum computing are: breaking encryption. Quantum computers could potentially crack some of the most widely used encryption methods, such as RSA and ECC, that rely on the hardness of factoring large numbers or finding discrete logarithms. This could pose a serious threat to cybersecurity and data privacy, but also open new possibilities for secure communication using quantum cryptography. Simulating molecules. Quantum computers could potentially simulate the behavior and interactions of molecules with high accuracy and efficiency, enabling discoveries and innovations in fields such as drug design, material engineering, and renewable energy. This could also help address some of the global challenges such as climate change and food security. Optimizing problems. Quantum computers could potentially solve some of the most difficult optimization problems, such as traveling salesman, vehicle routing, or portfolio optimization, that have many possible solutions and require finding the best one. This could improve efficiency and performance in sectors such as logistics, transportation, finance, and manufacturing. Quantum computers can be classified into different types based on their physical implementation and their level of error correction. Some of the main types of quantum computers are: superconducting qubits. These are based on superconducting circuits that can behave as artificial atoms with two energy levels corresponding to 0 and 1 states. Superconducting qubits can be coupled by microwave pulses and controlled by magnetic fields. They have relatively high coherence times, the time that qubits can maintain their quantum state, and scalability, the number of qubits that can be integrated on a chip. Some of the leading companies in this field are IBM, Google, Intel, and Rigetti. Trapped ions, these are based on individual atoms that can be trapped by electric fields and manipulated by lasers. Trapped ions have two internal states corresponding to 0 and 1 states. Trapped ions can be entangled by exchanging photons and controlled by laser pulses. They have relatively long coherence times and high fidelity, the accuracy of performing quantum operations. Some of the leading companies in this field are IonQ, Honeywell, and Alpine Quantum Technologies. Photonic qubits, these are based on individual photons that can be generated by lasers or other sources. Photonic qubits have two polarization states corresponding to 0 and 1 states. Photonic qubits can be entangled by beam splitters and controlled by optical devices. They have relatively low decoherence, the loss of quantum information due to interaction with the environment, and high speed, the rate of performing quantum operations. Some of the leading companies in this field are Xanadu, PsiQuantum, and Quantum Machines. Obstacles and limitations of quantum computing. Quantum computing faces many technical and practical challenges that need to be overcome before it can achieve its full potential. Some of the main obstacles and limitations of quantum computing are noise and errors. Quantum computers are very sensitive to noise and errors that can arise from various sources, such as thermal fluctuations, electromagnetic interference, or imperfect control. Noise and errors can degrade the quality and reliability of quantum computations, leading to incorrect or meaningless results. To mitigate this problem, quantum computers need to implement error correction techniques that can detect and correct errors using additional qubits and operations. However, error correction is very costly and complex, requiring a large overhead of resources and time. Scalability and connectivity. Quantum computers need to scale up the number of qubits and operations to perform more complex and useful tasks. However, scaling up quantum computers is very challenging due to physical constraints, such as wiring, cooling, or fabrication. Quantum computing is a revolutionary technology that promises to solve some of the most complex and challenging problems in science, engineering, and business. Quantum computers use the principles of quantum mechanics, such as superposition and entanglement, to manipulate information in ways that are impossible for classical computers. Quantum computers can potentially perform tasks that would take classical computers billions of years in a matter of seconds. However, quantum computing also has a bad side that poses serious risks and challenges for society, security, and ethics. Some of the bad sides of quantum computing are: quantum computers can break current encryption methods. Most of the encryption methods that protect our online transactions, communications, and data rely on the difficulty of factoring large numbers or finding discrete logarithms. Quantum computers can solve these problems much faster than classical computers, using algorithms such as Shear's algorithm or Grover's algorithm. This means that quantum computers can decrypt any information that is encrypted with current methods, such as RSA or AES. This would compromise the security and privacy of individuals, organizations, and governments. Quantum computers can create new ethical dilemmas. Quantum computing opens up new possibilities for creating and manipulating artificial intelligence, biotechnology, nanotechnology, and other emerging fields. These fields have enormous potential for good, but also for evil. For example, quantum computers could enable the creation of superintelligent AI that could surpass human intelligence and control. Quantum computers could also enable the manipulation of DNA and genes, creating new forms of life or altering existing ones. Quantum computers could also enable the development of new weapons of mass destruction or cyber attacks. These scenarios raise ethical questions about the responsibility, accountability, and morality of using quantum computing for such purposes. Quantum computers are difficult to build and maintain. Quantum computing is still in its infancy and faces many technical challenges and limitations. Quantum computers require extremely low temperatures, high vacuum, and isolation from any external noise or interference to preserve their quantum states. Quantum computers are also prone to errors and decoherence, which destroy their quantum properties and affect their performance. Quantum computers also need a large number of qubits to perform useful computations, but scaling up qubits is not easy. Quantum computing is a rapidly emerging technology that harnesses the laws of quantum mechanics to solve problems too complex for classical computers. In this podcast, we will explore how quantum computing can change the world and what are some of the challenges and opportunities it presents. Quantum computing is based on the concept of qubits, which are units of information that can exist in a superposition of two states, such as 0 and 1. This means that a qubit can encode both 0 and 1 at the same time, unlike a classical bit that can only store one value. By manipulating qubits with quantum gates, quantum computers can perform parallel computations and exploit quantum interference effects to achieve speedups over classical computers. One of the most promising applications of quantum computing is cryptography, which is the science of secure communication. Classical encryption schemes rely on mathematical problems that are hard to solve for classical computers, such as factoring large numbers or finding discrete logarithms. However, quantum computers can use algorithms such as Schia's algorithm or Grover's algorithm to break these schemes in polynomial time, rendering them insecure. This poses a threat to the security of many systems that rely on encryption, such as online banking, e-commerce, or blockchain. To counter this threat, researchers are developing quantum-resistant encryption schemes that are based on problems that are hard for both classical and quantum computers, such as lattice-based cryptography or code-based cryptography. These schemes are expected to provide security against quantum attacks, but they also have drawbacks such as larger key sizes or lower efficiency. Another approach is to use quantum cryptography, which is based on the properties of quantum physics, such as entanglement or no-cloning theorem. Quantum cryptography can enable secure key distribution or secure random number generation, but it also requires specialized hardware and infrastructure. Another promising application of quantum computing is a simulation, which is the process of modeling complex systems or phenomena using computers. Classical simulation methods often face limitations, due to the exponential growth of computational resources required to simulate large or complex systems. For example, simulating the behavior of molecules or materials at the quantum level requires solving the Schrödinger equation, which is intractable for classical computers. However, quantum computers can use algorithms such as variational quantum eigensolver, VQE, or quantum phase estimation, QPE, to simulate these systems efficiently and accurately. Quantum simulation can have significant impacts on various fields of science and engineering, such as chemistry, physics, biology, or medicine. For example, quantum simulation can enable the discovery of new drugs or materials by exploring their molecular structures and properties. Quantum simulation can also help understand fundamental phenomena such as superconductivity or quantum phase transitions. Quantum simulation can also provide insights into cosmology or particle physics by simulating exotic states of matter, or high-energy collisions. Quantum computing is not without challenges and limitations. One of the main challenges is to build scalable and reliable quantum hardware that can operate with low error rates and long coherence times. Quantum hardware is very sensitive to noise and interference from the environment, which can cause errors or decoherence in qubits. To overcome this challenge, researchers are developing techniques such as error correction or fault tolerance to protect qubits from noise and correct errors. Researchers are also exploring different physical platforms for qubits, such as superconductors, ion traps, photons, or atoms. Another challenge is to develop efficient and robust quantum software that can run on different types of quantum hardware and perform useful tasks. Quantum software involves designing quantum algorithms that can exploit the advantages of quantum computing while avoiding its drawbacks. Quantum software also involves developing quantum programming languages and frameworks that can abstract away the low-level details of quantum hardware and provide high-level functionalities and interfaces. Quantum software also involves developing quantum applications that can solve real-world problems and provide value to users. Quantum computing is a revolutionary technology that can change the world by solving problems that are beyond the reach of classical computers. Quantum computing has many potential applications in cryptography, simulation, optimization, machine learning, artificial intelligence, and more. However, quantum computing also faces many challenges and limitations that require further research and development. Quantum computing is still in its infancy stage, but it is rapidly advancing and attracting interest from academia, industry, government, and society.